Welcome to Lecture 8B, entitled Small Signal Modeling Procedure and Examples. So this is now the extension to Lecture 8A, where we'll work out some examples, and we'll tie it to something which you're familiar with. That is basically looking at a circuit equation, but looking at its dynamics. In ECE 212, you've already learned certain techniques of dealing with circuits, so I'll assume you know them, and just briefly go through the examples. So the material is basically for this lecture comes from Reading Assignment 2, Introduction in Section 2.1. And as stated in the previous lecture, what's the objective? It's to develop the procedure for determining the time evolution of a dynamic equation consisting of state variables, inputs and outputs for small perturbations about a DC equilibrium operating point. But we'll work through an example in this case. Concepts and definitions are the DC equilibrium operating point and the small signal model. Now, I'll just make a note. It would be very helpful for you to look at tutorial video 4 assigned for this week at the same time, because the material in the tutorial is complementary to this lecture. Again, we'll just briefly skirt over the second slide. It just gives you the breakdown of the individual slides to follow. I just make a note at the bottom that item 9 is optional reading and viewing, and it will not be tested. So you can just as well skip it, but I'll go through it because in future years you might find it very useful to basically know how we actually non-dimensionalize differential equations, and there are good reasons for doing so. More or less, it's a numerical issue. Okay, so let's take a simple circuit problem, and we're going to use this as our basis for exploring the notion of small signal analysis. So this is an example of state-space equations and output equations for a two-state variable, two-input, two-output problem. And the objective is to develop the state-space equations and out equations for the circuit below. That's our starting point. We basically need a state-space equation. All right, so if you look at this circuit, you'll notice, for instance, that I have inputs, U1 and U2. And as you'll see, I've already set this problem up in such a way that U1 is the sum of a DC value and a perturbation value. Same with U2, a perturbation value. Now, I should be doing this for all of these things, but there's too much clutter. So X1 would be X10 plus X1 hat. X2, which is here, state variable, would be X20 plus X2 hat. Y2 would be Y, capital Y subscript 2 plus Y2 hat, and this Y1 would be capital Y subscript 1 plus Y1 hat. Basically, those are things that replace these individual variables that you see here. Now, this is a circuit equation, and so you can identify two loops here, which we'll use to actually develop the state space equations. So there's one here and there's one here. And just by inspection, we can determine how many state variables there are. Just count the number of energy storage variables, and that will tell you how many state variables. So we have an inductor and we have a capacitor. And so the state variables, there'll be two. One associated with the current flowing through the inductor and one with the voltage across the capacitor. So again, this is just a summary of what these different variables are. Output variables in this case would be the inductor voltage, Y1, and the voltage across resistor R1. Again, this is just for purpose of example to show you the process. I could have chosen output variables to be different, but it's just simple in this case to just use this as an example. Now, the nodal point is of interest because we'll be able to use both Kirchhoff's voltage law for this loop, and Kirchhoff's current law to express the current in this branch in terms of the current in this branch, and this branch. So this is more a question of using the knowledge you've developed from circuit theory to set this the equations up for this system, but these would be the dynamic equations. All right, so here's basically the procedure for doing it. So for loop 1, we basically sum the voltages around the loop, and that's the equation that you see here. U1 minus the inductor voltage minus X2, which is the capacitor voltage, equals 0. The second was loop 2 is U2, that's the input voltage U2, minus R1. And this is the current that's flowing through here. And you get that current by applying Kirchhoff's current law at this nodal point here. Minus X2 equals 0. So here are your two equations, the state variable x1 and state variable x2. But typically, we're interested in putting this equation in the standard form where you only have dx1 dt on one side and all the variables and other things, inputs are on the other side. Similarly here. So this is basically what I've done out here. I've basically simplified the equation such that dx1d is on this side, and you get this expression, and dx2 dt looks like this. Okay, what about y1 and y2? Well, you can express y1 and y2 in terms of input variables and output variables, again, just by applying Kirchhoff's voltage law. If you go around this loop, you can express y2 in terms of u2 and x2, and if you go around this loop, you can express y1 in terms of u1 and x2, which is what we've done up here. So this basically then is the starting point where we have our state space equations. All right, so this is the first thing you need to do right off the bat. All right, because these are linear equations, we can also represent those state space equations in matrix form, which is what I've done here. And so you can see here's a matrix times the state variables in column form. And there's another matrix times the input variables in column form. And we'll call this one the A matrix and this one the B matrix. And so this is what you would see if you put it in equation form. This is the final expressions that you would see. If you multiply everything out, it would look like this. So this and this are equivalent. It's just a different form of representation. In the output equations, again, what you can do is just take the group terms. You can put it in matrix form because we're dealing with linear equations. Or you can write it in the classical form in terms of functional form. And this already was written like this on the previous page. So your choice, either this way or this way, right? This way or this way. But this is only valid if both systems are linear in the state variables and the input variables. All right, so now next step is to determine the equilibrium values, the operating points. And they're derived by knowing what the input equilibrium value is. So that's a given. So you're given inputs U1, T, U2, and you're saying they're constant DC signals, U1 capital, U2 capital, respectively. So now what we need to do is to figure out what are the equilibrium values for the state variables, right? So we want to know what x10 is for x1t and what is x20 for x2t. We also need to know the equilibrium values for the output variables, which is y1t equals capital Y subscript 1, y2t is capital Y subscript 2. So how do we do that? Well, if there's no change taking place, that means the derivatives with respect to time are equal to 0. So you end up with 0, 0. And you're interested only in the steady state variables. So the x1 becomes x10, x2 becomes x20. U1 and U2 capital are basically your input steady state variables for the input variables U1 and U2. So here we have basically, these are given. x10 and x2 are knowns. You have two equations and two unknowns. Because it's a linear equation, of course, there'll be only a single solution to the problem. And so you can solve, in this case, for x10 and x20. Similarly, for the output, you have basically a steady state for y1 and y2. Once you've computed x10, x20 from here, then you can substitute that in here and compute what the steady state variable values for capital Y subscript 1 and capital Y subscript 2 are. Okay, so here we basically now do the actual, put the numbers in, and so you just go to a couple of slides previous to this one. 0, 0 is equal to this, okay, and if you basically look at this, this is nothing more than the right-hand side of the state space equation, but with the equilibrium value substituted. So there's what we've got. And so these two equations, this one and this one, have to be solved, and both of them are equal to 0. The matrix form of this equation would have this form. This times this plus this equals 0, 0. That's taking this and putting it in matrix form. Now, if we're in matrix form, basically, we want x10 and x20. So we could take this and put it on the other side, in which case you get minus this matrix. And then if we multiply left and right by the inverse of this matrix, then we end up with the expression that you see here. Okay? All right, so this mate inverse, if you do the calculation, is this. So now we can basically go ahead and actually compute what x1 naught, x2 naught are. And so that's what I've done here. So this is that and times that from the previous page. If you multiply these matrices through, you'll end up with this expression that you see here. Okay, now you can write this out in this classical form, state space variable equation form. You just say x1 is equal to this times u1 minus this times u2, which is what I've done here. And x20 is equal to u1, which is what you see here. Now you could have also done this by inspection, because what you would do is basically take the existing circuit that you had and do the DC circuit model. And the DC circuit model essentially would mean all inductors are shorted, all capacitors are open circuited, all voltage sources that basically are non-DC are shorted, and all current sources which are non-DC are open circuited. If you go back to the original circuit that we had and perform that task, then this becomes the DC equivalent circuit. Now, if you were to solve this problem here, right, then you could solve for x1 naught and you could solve for x2 naught, and you would end up with these equations here, just using this diagram. So that's a sort of a nice way of doing things from the picture format rather than from the mathematical format. Okay, so next step, basically, we've got our operating points. Now we have to deal with the small signal. So this is a slide which I'm repeating again. So small signals, basically, we said U1 is replaced by U1 steady state plus small perturbation. Similarly, U2. And these are functions of time. Small signal state variables and inputs. So here we would have the state variable x1 replaced by its equilibrium value plus a perturbation. x2 is replaced by its equilibrium value and a perturbation. And y1 basically and y2 similar. Steady state plus perturbation, steady state plus perturbation. So, as I said, x1, x2 are referred as state variable operating points. y1, y2 are referred to as output variable operating points. Okay, so now basically we do the small signal differential equations and output equations. And so we take the original equations that were given, state space equations. We replace x1 by this, we replace x2 by this, we replace y1 by this, y2 by this, u1 by this, and u2 by this. And these are the expressions that we end up with. Recall from previous lecture that this being constant, the derivative of this first term is 0. So we're just left with this term here. Similarly, derivative of this is 0, so you're just left with this term. And so we just make the substitutions in here as shown. And so this now sets us up to solving the problem. All right, so now we make use of a Taylor series expansion of the state space equation only out to first order. And so on the right-hand side, we had basically a function of, in this case, 4 variables. This is one variable set, second, third, and fourth. So when we basically do expansion to first order, the first term is the constant value at the operating point. And the linear terms would be linear in this one, this one, this one, and this one. So effectively, we need to take the partial derivatives with respect to the variable of interest, right, times the small signal perturbation. Okay, so this is a classic Taylor expansion. So here's the constant term. Here's the contribution to do U1, perturbation, U2, perturbation, X1, perturbation, X2, perturbation. It's 4 variables, and so there are going to be 4 derivative terms and 4 perturbation terms. You do it basically for the first state space equation, you do it for the second state space equation. All right, so this is basically the procedure that we go through. All right, so here we basically have spelled it out. We can basically put this into matrix form because everything is linear now. These are linears. These are simple linear perturbation values. And so you see these derivatives all come together. Everything associated with U1, U2, you can see is with respect to partial derivative with respect to U1s and U2s. And everything involving the state variables is with respect to partial derivatives x1 and x2. So a matrix here and a matrix here. But these matrices have partial derivatives. So in fact, as we mentioned in the previous lecture, these are basically the Jacobians. They have the look of a Jacobian matrix. And so we basically just write everything out in a sort of compact form. Here's the equilibrium value. Here's the first order term, involving only state variables, involving only input variables, perturbations. And the JF and BF are matrices. This is a Jacobian matrix, and this is a Jacobian matrix. We also have that the equilibrium value from previously, that dx1 by dt is equal to 0 is equal to this. So if this is 0, 0, then this term basically doesn't exist. It's equal to 0. So finally, we end up with a small signal model that looks like this. All right, so this is a final result for the state space model, the small signal, only in terms of small signal perturbations. All right, we do it also for the output now. We just do the perturbation. And if we go through the same procedure, expand out, right, you'll end up basically again with a new matrix, a new Jacobian matrix for the output, which because it's a different function g. And you'll have terms, Jacobian involving the input signal perturbations. The equilibrium point basically is just the values of the equilibriums put in here, which is y1 over y2. And in this case, basically, we can just write that the small signal component, y hat 1, y2 hat, is just going to be the parts that are contributions from the the state variable perturbations and the input variable perturbations. So these matrices are different than the matrices that are associated with the state space equations. But again, because they have partial derivatives in matrix form, we call these Jacobian matrices. Okay, so let's do the example of the small signal model for the state variables and output equations. So we have it this form. And the JF basically, we can do the computations and we'll find that we end up with this for JF and this for BF. And so the small signal model basically just involves these matrices substituted in here. All right, and so the output small signal perturbations would involve these Jacobian matrices, which we can calculate. It's just this one here and this one here. Now, as far as a small signal model, we can also show what the picture form would be from which we could actually have gone back and derived these equations. So in that case, what do? We would basically short the DC sources. So in this case, there are two DC sources. They'd be shorted. All right, and basically retain everything else. And so this is the final circuit that you would get. So if you basically were to solve this circuit equation, which is our small signal model, then basically you would end up with this differential equation. All right. Now this is nice because it's linear. We would not be able to do this as of a nonlinear system. All right. Then we basically have to stick with the equations and just be a little bit more careful in terms of how we do things. All right, so just a general question of interest, the special case of large and small signal model being equivalent. So sometimes the small signal model and large are equivalent to each other, which is the case if you're dealing with linear systems, because they're exactly the same problem. So the original state space equations for the linear system looked like this. The small signal model for state equations looked like this. But look at the matrix for JF versus the original matrix. They're the same. Similarly, this matrix and this are the same. So the large signal model and the small signal model for a linear system are identical to each other. Similarly, if we look at the output equations, this was the original equations. These are the small signal equations. But this is all linear, and you'll notice that this and this are equivalent, this and this are equivalent. So, special case. Large and small signal models for linear systems are identical. All right, so at this point, you could probably stop viewing this lecture. I'm just going to spend a little time on these remaining couple of slides dealing with how we take differential equations and basically make them non-dimensional. We did this in one of the previous lectures when we dealt with sensitivity analysis, in which case basically we created per unit equations. Well, we can do the same thing in this case. So consider the following differential equation. It has this form. So we want to convert it into a non-dimensional form. So there are a number of steps we need to take. First is we need to determine a base unit or normalization factor for all of the variables in the systems. Right? The variables include the time. So you have x, you have u, and you have t. That's these. And then you have to select normalization factors, which is really up to you. It's your choice, whatever's convenient. So we call u base capital U, x base capital X, t base capital T. And then we're going to define per unit variables for u, x, and time t as the follows. U over u is just taking u and dividing it by a normalization factor. This has no units. Same with xu, same with tu. And now what we do is we introduce the base expressions from this back into the differential equation. And you'll see what I've done here. Basically, xu times x basically brings you back to x. Tau times t brings you back to t. U times u brings you back to u, and xu times x brings you back to x. So this is basically, through substitution, we have this. Now what we do is multiply both sides of the last equation, that's this one, by t, and divide the last equation all through by x on both sides to obtain the following non-dimensional differential equation. Tau has no units, xu has no units, uu has no units, xu has no units. If you look at the units of these combined constants, they have no units. If you look at the combined value of these two have no units. So this is now a per unit differential equation. Okay, so this is just the notes that I mentioned earlier. All right, here's another example. This is a differential equation. L di by dt is equal to v minus IR. This is a series LR circuit. How do we convert this into non-dimensional form? Same procedure. We need to determine a base unit normalization factor for current, voltage, and time. So V base is some V. I base is going to be V base divided by R. Okay, R is given. We've chosen that as a base for current. I mean, you can choose something else, but this is a convenient one to choose. And T base we're going to choose as L over R as a base for time. In fact, if you look at the ratio L over R, it has units of time. All right, so this is just convenient to use. And so now we define per unit variables for voltage, current, and time. VU is V divided by V base, IU is I divided by I base, and TU, which we'll call tau, is T over T base. So now what we're going to do is divide differential equations on both sides by R and introduce base expressions for 3 into the differential equation. So I've divided this by R, which gives me this. And now basically I introduce for I this expression, for T this expression. Okay. I base minus IU I base. Okay. And so this is the expression that I get. Now we divide the last equation, this one here, through by I base on both sides, and we obtain this equation. So this basically is per unit, that's per unit, and that's also per unit. Okay, so this was just an example of how I produced per unit equations. All right, so now here's another one, RC series circuit. Let's basically convert this into non-dimensional form. Again, same procedure. The normalization factors here are going to be more or less the same, except for the last case I chose T base to be R times C, and this has units of time. All right, so again, we've defined the per unit variables as such. In this case, V per unit is V over V base, I per unit is I over I base, and T, which is called TU, which is also tau in this case, is T over T base. We introduce these base expressions from 3, okay, that's these ones, into the original differential equation. Okay, so just substitute for V, right, and for T, right, and what do we end up with? There's the substitution for V, for T, V basically minus VU V base. Okay, so divide the last equation through by V base on both sides, right, and we end up with this per unit equation. All right, so the last case I'm going to deal with is an LRC circuit. That's an inductor, capacitor, resistor in series connect to a voltage source. In this case, there are 2 storage elements, so there'll be 2 differential equations. In fact, you could make them into state space equations if you want to. So there they are. This is KVL, and this is basically KCL. So in this case, we need to determine a base unit for I, V, and T. And we're choosing the normalization factors in this particular fashion. It's convenient, but there are others you could choose. Just make sure units are correct. V base is going to be our base voltage. I base is going to be V base divided by the square root L over C, right, as our base current, and T base is the square root LC. We're going to choose that as our base time. All right, so we choose our per unit variables by just dividing through the bases as we've done before. And now what we do is multiply the first differential equation by root C over L and the second differential equation by root L over C, and introduce base unit expressions from 3, that's from here, into the differential equations. So for the first differential equation, we'll end up with this. And now after making substitutions for the base quantities, we end up with this expression here. Similarly, for the second equation, we basically do the same thing. We make substitutions for V, substitutions for T, and basically substitution for I, and then we end up basically with this expression that you see here. Next step is divide the first equation through by I base on both sides, and the second equation through by V base on both sides, from which we then obtain the per unit non-dimensional coupled differential equations. Coupled meaning that the state variables of both appear in both the differential equations. So here we have now everything in per unit form. If you look at square root C over L, that's 1 over an impedance. R is an impedance, so this has no units. No units, no units, no units, no units. And here, of course, no units as well. Okay, so that concludes Lecture 8B. Thank you for listening.